10 students. So this is my next video, which is basically related to satellite subsystems. In this video, we will study about different part of satellite and the earth station. So these are the contents that I am going to cover today. The basic overview, AOC subsystem, TTC and M subsystem, power subsystem, antenna subsystem and communication subsystems. Let's start with the basic introduction. We all know about satellite, like we have some earth station, we have the satellite part, and we know that the cost of satellite will increase based upon the part of the satellite which are there on the satellite. So the overall launching and the complete process will be expensive if we place a number of heavily loaded objects and instruments on the satellites. So that is why the type of satellite system or subsystem plays a very important role in satellite communication. Let's have the look of satellite subsystems. Here we can see in this picture, we have this complete structure of your satellite. As you can see in normal videos and in pictures, this is the solar panel that we can see here. These are the solar panels, and here we have different type of antennas which are placed on the satellite. One is X-band antenna, GPS antenna, then we have the camera, we have the tracker, we have the payload equipment. So these are the different parts of satellite. Okay. So basically, what is subsystem? A subsystem that must exist in all satellite in the communication subsystem, which enables your spacecraft to communicate with the ground station. So each and every small bit of this subsystem plays a very important role in the whole process of your satellite communication. Broadly, we can categorize our satellite subsystem into three major parts. First is the space segment, second is the user segment, and third is the control segment. So space segment is the part of your satellite subsystem which is there on the space, okay, which you have launched and which will be there in the space or in the orbit. So that is your space segment. See, only your space segment cannot complete the process or cannot do the communication. So what we need a ground station which will basically control the overall process of your satellite communication. So our ground station or the earth station can have two major parts. First is the user segment and second is the control subsystem. What is this user segment? User is the end user which will be utilizing that services of that satellite communication. Maybe a user can be mobile, it can be stationary, your user can be in any aircraft, user can be in a ship, or user can be on land in a moving vehicle, right? So your end user can be in any form. It can be mobile or it can be stationary. So that part is your user segment. Next is the control segment. So we have majorly your satellite subsystems will be controlled by your control segment, in which you have the tracker, you have the commanding subsystem, which we will be discussing later on. Okay, so we have the control segment. So these are the three major segments of your overall satellite subsystems. This I have already covered. Now, our satellite subsystem can broadly be classified into 5 major types. First is the AOC, second is the TTC and M, then is the power subsystem, then next is the antenna subsystem, and the last one is the communication subsystem that I have shown in the first slide. So let's have a look of AOC subsystem. So what AOC means? AOC means the altitude and orbit control subsystem. See, your satellite is placed in one orbit, right? So it is not always the case that your satellite will keep on moving in the same orbit because of so many external environmental effects, gravitational force of sun, moon, atmospheric drag. Your satellite can deviate from the correct orbit. So orbit can be changed, right? Because of so many effects. So we have to make some arrangement so that your satellite would be there in the same orbit and it would be at the correct position. So we have a system which is known as altitude and orbit control subsystem, which will monitor, check everything about the current position, and if your satellite deviates or drift from that current position, then it will revert it back to the actual position. Okay, so broadly your AOC can be characterized into two major parts. First is the altitude control subsystem and second is the orbit. What is altitude? Altitude I have already covered in my previous videos. Altitude is the height of your satellite from the surface of Earth. Let's say this is Earth and here your ground station is there. So the height of satellite from the surface of Earth will be your altitude of the satellite. So how we can control the AOC? So AOC can be controlled by two major methods. First is the by spinning the satellite and second is the by using 3-axis method. So this can be characterized based on the type of satellite. In the satellite where we use the spinning process, those satellites are known as spinners, and in satellites where we are using this 3-axis method are known as 3-axis satellites. Here you can see the picture of the real picture of two satellites. First is a spinner satellite, which is actually your Intelsat 4A, and second is the 3-axis satellite, which is your Intelsat 5. Okay, so here this is a drum-like structure, and these are the solar panels which are there on the satellite, and these are the antennas and the transponder. In 3-axis satellite, there is no drum-like structure. Your solar panels are kept in a form of wings. So these wings will be open, and here we have the antenna and transponder and the rest of the part of your satellite. So here these are the solar panels. So in this type of satellite, we use the 3-axis method, and in this type of satellite, we use the spinner to control the orbit and the altitude of your satellite. Now, what is this spinning of satellite? What do you mean by spinning? Spinning, student, means the moving or the rotation, right? So there would be, by spinning the satellite, what we do, we generate a force which is known as a gyroscopic force, and with the help of these gyroscopic force, what we do, we drift the satellite to its correct position. Okay, so that rotation can be of 3200 RPM of that spinner. And the satellite which use this type of method for controlling the correct orbit and the altitude of satellite are known as spinners. And here there would be a drum which is also called the cylindrical form of drum, and your this drum is covered with the solar cells. Power systems and rockets are present in this drum itself. Now, with the help of spinning and de-spinning, what we can do, we can control our satellite and we can place our satellite in the correct orbit. See, this AOC subsystem cannot do in a standalone way. What it does, it actually takes the help of TTC and M subsystem, which I am going to cover in the next coming slides. So it actually works in collaboration with TTC and M to control the orbit and the altitude. Now moving on to the next type, which is a 3-axis method. In 3-axis method, we can stabilize our satellite altitude by providing the momentum wheel. Okay, so there are momentum wheels which are there, and this method is called 3-axis method because here your satellite position is controlled by controlling 3 orbits, 3 axes. First axis is known as roll axis, second axis is known as yaw axis, and the third axis is known as the pitch axis. Okay, so what is this roll axis? Roll axis is considered in the direction in which the satellite moves in the orbital plane. So if this is your satellite, okay, and if it is moving in this direction, so your roll axis will be in this direction itself, right? Second is the yaw axis. Yaw axis is considered the direction towards the earth. Okay, so here we have earth, okay, here we have our earth station. So the direction towards earth is known as the yaw axis. Now third is the pitch axis. So pitch axis we consider the direction in which is perpendicular to the orbital plane. So direction perpendicular to the orbital plane will be known as the pitch axis. So by controlling these 3 axes with the help of momentum wheel, we can place our orbit in the correct orbit if it is drifted. So in this picture, you can see the 3 axes, students, yaw axis, and then roll axis and the pitch axis. So by rotating these 3 axes, we can place our satellite in the correct orbit. Next is the orbit control subsystem. The orbit control subsystem is useful in order to bring the satellite back into its correct orbit whenever your satellite gets deviated from that orbit because of external effect. So as I told you, like this AOC system work with the TTC M, which is present on Earth station. So what it does, TTC M system, the part of TTC M subsystem which is present on the Earth, will monitor the satellite position, and if we find any sort of change in its orbit, then it will indicate some signal to the AOC, and then AOC system will start working, its motor will start working, and accordingly your satellite will be drifted back into the correct orbit. So this is how your AOC system, complete system works. Now student, we are moving towards the next subsystem, which is known as TTC M subsystem, and I need to mention it that this is very important subsystem, okay, because it is you can say the main subsystem which is used to control the complete operation of your satellite. And the part of this TTCM is not completely there on the Earth station or not completely on the satellite. There are some part which is placed on the satellite, and there are some part of the system which are there on the Earth station. So what does it mean, TTC and M? So TTC and M stands for telemetry, tracking, commanding and monitoring subsystem, and each and every word of this has a significant role in this subsystem. TTC and M is telemetry, tracking, commanding and monitoring. So part of this TTC and M are there on satellite and on Earth station. Okay. So before moving ahead with TTC and M, we should have the knowledge about what is telemetry, what is monitoring, what is tracking. We all know what is telemetry. Telemetry means sending some data or sensing some information and then send that data to a different location or to a remote location. That is known as the telemetry. Okay. Telemetry. So telemetry means measurement at a distance. So mainly the following operation takes place in the telemetry. What are the measurement? See, we have to check the operation of complete satellite. So how we will get to know about the complete operation of your satellite? We will get to know with the help of some sensors which we place on the satellite. And what are the purposes of these sensors? So these sensors will sense the overall external environment of your satellite, its current position, its temperature, pressure and other things. So the sensor will sense that information, and then we encode those information into the correct form of electrical signal, and then we transmit that code to a far distance. So this is the purpose of your telemetry subsystem. Now coming to this picture. So this picture, this block diagram is very important. This is the block diagram of your typical telemetry command monitoring subsystem. So I'll explain each and every block of this subsystem. Here you can see this is the satellite, and this is the TTC and M antenna which is placed on the satellite part. First, your satellite will sense some information with the help of sensors, and all those information about your pressure, about temperature, about everything will be converted into the correct form of data, and that data will be transmitted with the help of this transmitter, TTC and M transmitter, and then it will be received by the Earth station. So here this part is your Earth station part. Okay, and this is your satellite part. Right? This is our satellite part and this is our Earth station part. So your signal is transmitted to the Earth station. Here we have the Earth station antenna which will receive those information. Okay, and what that information is, there would be some information about the temperature, pressure and other external effects, and there would be some information about the position of your satellite. So the information related to telemetry will be given to the telemeter receiver, and the information about the position of your satellite will be given to the tracking system. Then what we will do, we will process that data with the help of data processor, and then we will provide that information to the computer which is there for AOC. So telemetry information and tracking information, both the information will be given to the computer or the processor for AOC. What is the purpose of this AOC computer? It will give this information to the commanding transmitter and the controller. Okay, so both the information will be given to the commanding transmitter and the controller. Now, what this transmitter will do, this information about the AOC, like what function AOC has to do or what operation AOC has to do, will be transmitted by this transmitter to the antenna and further to the satellite. So accordingly, we found like my satellite is not in the correct orbit, we need to shift that orbit little bit. So that information will be given to the AOC, and accordingly this AOC will generate a signal or give a command to the satellites, and then the motors or the thrusters placed on the satellite will work accordingly, like how much tilt it has to give to the satellite so that it can be in its correct orbit. Similarly, if there is a sudden high in temperature or low in temperature, so that information which we have received from telemetry will also be given to this transmitter, and further this transmitter will give that information to the satellite that yes, you need to change the temperature of the component or you need to change the pressure of that component. So accordingly your satellite will act. So here you can see that this TTC and M work along with your AOC subsystem. So this complete explanation I have already given to you. Okay. Now coming to the next, which is the power subsystem. Power subsystem means the subsystem which will provide you the enough power so that your satellite components can work properly. So what is the arrangement of power on satellite? Very simple. We are using the solar arrays or solar panels for that. Why? Because there is no other source of power, or there is a life of satellite of around 10 to 15 years. So we cannot place so much burden on satellite of batteries or something so that it can work for such a long time. So what we do, we utilize the solar energy to provide the electrical signal to the satellite. So there are mainly different type of solar arrays that we are used. We have cylindrical solar arrays and we have normal rectangular solar arrays. Cylindrical solar arrays are there, which I have already discussed on, used in the spinner. So these are the cylindrical solar arrays, and these are the rectangular solar arrays which are there in the 3-axis satellites. Okay, so power will give you the enough power with the help of solar panels. Okay, so there are two terms that you should know about this satellite, that is the beginning of life and the end of life. So actually once the beginning of life means once a satellite is launched in the correct orbit, it is placed in the correct orbit and it started its working. So that is known as the beginning of life. So at the beginning of life, your solar panels work very efficiently, and the maximum efficiency we can see with the help of solar panels is around 25% in the beginning of life. End of life means after 10 or 15 years that solar panel efficiency goes down, and by EOL it comes down to around 15%. Okay. See, there are two things in solar panels there are some issues, like once there is a solar eclipse, so there is no enough sunlight available on the satellite by which you can get the enough power. So we are also providing the facility of rechargeable batteries there. Why we are using rechargeable batteries? Because we cannot get sunlight in the solar eclipse time. Okay, and these are rechargeable batteries which we can recharge. Okay, and we can provide the enough power to our satellite subsystems. Now moving on to the next subsystem, which is antenna subsystem. Okay, so as we know that antenna can be on satellite, antenna can be on earth station. Okay, and depending upon the usage, your antenna type will be different. Okay, depending upon the application, your antenna type will be different. Here a question arises, why we are using a frequency range of gigahertz in satellite communication? Why not megahertz? Why not lower frequencies? So the reason of using this gigahertz frequency range on satellite communication is, as we know that there is a relation between the antenna height and the frequency. So we know that the length of satellite antenna is inversely proportional to the operating frequency. Okay, so length of antenna is inversely proportional to operating frequency. Hence, we have a limitation to put lower size of antenna on the satellite because of its size, because of its launching process, because of its the cost. So what we do, we need to place low length antenna and low size antenna on the satellite. So as there is a inversely relationship between the size of antenna and the frequency. So if antenna size goes down, then the frequency goes up. So that is why we are using a frequency which is of the range of gigahertz in satellite communication. Now, based upon different applications, we have different 4 categories of satellite antennas which are placed on the satellite. Okay, first is wire antenna, horn antenna, array antenna, and reflector antenna. Okay, what is this wire antenna? Here, this is the complete picture of satellite antenna. So this is not, I mean, it is not like only one type of satellite antenna would be placed on satellite. Depending upon different applications, multiple antennas are also placed on satellite. Few of them are working on C band, other antennas are working on KU band or KA band. So depending upon that, we are having a number of antennas on the satellite. Okay, so first let's talk about the wire antenna. Wire antenna is nothing but a very basic type of antenna which can be of monopole or dipole. Okay, so basically monopole and dipole, there are 2 types of wire antenna. These are used generally on the TTC and M subsystem. Okay, the length of total wire which is being used as a dipole, if equals the half of the wavelength, such an antenna is known as half wave dipole antenna. So if this condition satisfied, then the antenna type is known as the half wave dipole antenna. These wire antenna are omnidirectional antenna. And what is omnidirectional means? Omnidirectional means antenna which is radiating equal amount of radiations in all directions or provide signal strength in all directions are known as omnidirectional antenna. So these wire antenna are omnidirectional antenna. Here we have the picture of this wire antenna. Next is the horn antenna. Horn antenna is actually your antenna can have some aperture, okay, and this type of aperture antenna are known as aperture antenna, in which you have the aperture. The edge of transmission line when terminated with an opening radiates energy. So if this type of structure is there, so this is known as antenna aperture. Okay, this opening which is an aperture makes it an aperture antenna. Now, horn antenna is also an example of aperture antenna, and it is used in satellites in order to cover more area on Earth. So, to increase the coverage, we are using the aperture antenna. Horn antennas are used in microwave frequency range, hence the same feed horn can be used for both transmitting and receiving the signal. So, if the same horn is used for transmitting and receiving, then how it is possible? So it is possible with the help of a duplexer. What is the purpose of a duplexer? Duplexer is actually a device which works as a switch. Switch means it has both the facility, it can connect your antenna to transmitter, it can connect your antenna to receiver. So if you want to transmit a signal, your duplexer will switch to the transmitter. Okay, it means your antenna will be connected to the transmitter side. If you want to use it at a receiver side, then your switch will be connected to the receiver. So then your antenna will be connected to the receiver so as you can receive the signal. So with the help of duplexer, you can use your same antenna for transmission and reception. This is the structure of horn antenna you can see here. Then we have array of antennas. So array of antenna is not a type of antenna, it is actually a combination of multiple antenna. So because of the limitation, like if you want to increase the coverage of your satellite antenna, then what we do, we keep we provide multiple antennas, okay, all together so that we can increase the coverage. Okay, so single antenna cannot radiate enough amount of energy in a particular direction. So what we do, we collect multiple antennas all together and then we enhance the range of that single antenna. So here you can see the antenna arrays. Okay, these are the multiple antennas which are working as antenna array. Here also multiple antennas working as array of antennas. Then we have the reflector. So reflector antennas are generally known as a parabolic reflector, is a very important type of this reflector antenna, which are suitable for producing beams, okay, and it will provide you a directional service, like it provides you the energy in a particular direction. So that is why these are known as very highly directional antennas, okay. Parabolic reflector antenna is used for transmitting a signal in the form of feed, which comes out from a dipole or horn antenna to focus the wave on the parabola. So I'll explain with the help of this diagram. So this is the parabolic antenna reflector, and here we have the horn. So what is the purpose of this horn? It will direct, or it will focus the energy into this parabolic surface, and then it will radiate the signal. So that is how your reflector antenna work. Now moving on to the last type of this subsystem, which is known as the communication subsystem. So communication subsystem plays a very crucial role in your satellite communication in order to transmit or receive the signal, okay. The major device which is placed on the satellite for this purpose is known as transponder. Transponder means transponder, the definition of this transponder is like which can perform both the function transmitter and receiver in a satellite. So here its name comes like transmitter, we are getting trans, and from responder we are getting the ponder. So that is how its name has come, which is the transponder. So we can see the block diagram of transponder. General block diagram of transponder is this. The major purpose of your satellite on satellite is the transponder is to receive the signal, then amplify the signal, and then transmit back to the earth station. This is the normal purpose of your transponder. As your satellite work in two different frequencies, one for uplink, another one for downlink, so there is a change in frequency. So who will change that frequency? Like in case of C band, we have a frequency of 6/4 gigahertz. 6 gigahertz for uplink and 4 gigahertz for downlink. 6 gigahertz for uplink we are receiving at the satellite. Now who is converting that 6 gigahertz signal into 4 gigahertz? Because we need to downlink that signal at 4 gigahertz. So who is converting that signal? So transponder is converting that signal from 6 gigahertz to 4 gigahertz. This is the purpose of the transponder. Here we have the satellite antenna, which will transmit the signal to the duplexer, and here this is the earth station. At earth station we have the low noise amplifier, which is LNA, then we have the carrier processor, then we have the power amplifier. So we will explain this transponder with the help of this figure. This is a main figure of your satellite transponder, which is known as the single conversion transponder. I'll explain the working of this single conversion transponder considering a case of 6/4 gigahertz, okay, like a normal C-band signal. Here we have the earth station, which is transmitting a signal which is working at 6 gigahertz. Here we have, so this is actually the transponder. This is the transponder, and then again we have the earth station here, right? This is the complete satellite communication. Here we have the earth station, it will transmit the signal. Now at the satellite we have the transponder. So this antenna will receive the signal at a 6 gigahertz frequency. Then at transponder we have the LNA. LNA is low noise amplifier. The purpose of this LNA, which is low noise amplifier, also known as RF amplifier, is to amplify the each and every component present in the signal. Then we have a band pass filter here. The purpose of this band pass filter is to filter out all the components which are noise or unwanted signals, and to keep only 6 gigahertz signal with that. Now the purpose of this transponder is to down convert the signal from 6 to 4. How we will do it? We will do it with the help of this down converter. Okay, it is actually a mixer. It is nothing but a mixer. So it will mix two frequencies. One frequency 6 gigahertz, another frequency that we are generating with the help of local oscillator. Okay, students, just tell me, like to get a 4 gigahertz frequency, how we can get 4 gigahertz from 6 gigahertz? We can get 4 gigahertz from 6 gigahertz. If we minus 2 gigahertz, then we can get the 4 gigahertz signal. So this 2 gigahertz signal will be generated with the help of local oscillator, and this signal is coming from this side. Okay, so here we are having 6 and we are generating 2 gigahertz signal from here, which is approximately 2. It's not exactly 2 gigahertz because of the limitation of this local oscillator. This is not the ideal case, right? This is a practical case. So that is why we have considered 225 megahertz here. Now, after mixing, we are having two components. One is 6 plus 4 and one is 6 plus 2, another one is 6 minus 2. So 6 plus 2 will be filtered out with the help of this band pass filter, and 6 minus 2, which is actually the 4 gigahertz, will be passed through it. It means 4 gigahertz will be passed. Then we have the low power amplifier here. Then we have the high power amplifier here. And then as we have now the 4 gigahertz signal, so we will again downlink that signal to the earth station. This type of transponder are known as bent pipe transponder or single conversion bent pipe transponder, which work on the C-band frequency. Then in case of double conversion bent pipe transponder, we have the double conversion state. So this is the last slide I am explaining. So here we have the double conversion band pipe transponder, in which your frequency will be double converted, which we generally use in case of 14 by 11 and 30 by 20 gigahertz, means for KU band and KA band. So here we are receiving 14 gigahertz signal. Again we have the low noise amplifier, then 14 gigahertz band pass filter. Then what we do, we are providing two stage conversion. First is from 14 to 1 and then from 1 to 11. Why we are converting to 1 gigahertz? Because we need to provide some additional amplification with the help of this IF amplifier. So that is why we have introduced this IF stage here. So first your signal is down converted to 1 gigahertz by 14 minus 13. Then what we will do? We will up convert that signal with the help of this up converter. And finally your 11 gigahertz signal will be amplified and transmitted back to the earth station. So this is the complete communication subsystem. Thank you so much for listening.